All right, so page 43 is the chapter 8 homework part 3, and I had said you could skip this particular page, which was page 42. So let's look at 43. Okay, we had talked a little bit about this number 2 yesterday. So one of the things I want to make sure you're doing here is having this equation in context, and we knew that the calculus was our y because we were predicting calculus from the physics. Okay, and then you also have the putting in the physics score to get that predicted calculus grade. Okay, so there's that one. So number 3 was a problem where the question asked us to predict the number of fish species from the average pH level. So that was how we knew that our fish species was going to be our y. So there was the equation that came out from that. And then once you get this equation, and that has to be shown in context, then you can plug in this 7.6 to predict the number of species in that river. Okay, now on this problem, so here is a common issue that I want to point out to you. So when my students see a problem like this, here's the thing that I think just doesn't connect in their brains, okay? A table of values is giving you information that actually occurred, or a coordinate, this 73, 7.9, that's actual x and actual y. So then that's how you're coming up with this. You can then put the x value into the prediction equation to get that predicted y. And then from there, you're doing your actual y minus predicted y. Okay. And so that residual was negative 0.061. Okay. So I think that's the thing that gets kind of missed over. That doesn't click, and then we don't know where to go with that problem. All right. Number 5. Okay, so we had done this one yesterday in class when we were 2 days ago. We did it on Tuesday. So I actually want to kind of point out something to you. I want to talk to you about the difference between transformation of data affecting correlation and one particular point affecting correlation. So 2 days ago, we would talk about, adding or subtracting, multiplying or dividing to all of the data. So all of the values are multiplied by this, or all of the x's and y's are switched, or all of the values are multiplied, x's and y's are multiplied by this. Okay, that's a transformation to everything. Correlation then stays the same no matter what you do. Add, subtract, multiply, or divide. You can even switch the x and y. The only exception is if you multiply by one particular negative, a negative, that would just change the sign. That's the only thing that could change is the sign. For example, had you multiplied all of the y's by, say, negative 20, if you had done a transformation by negative 20 to everything, it still would have made the correlation the same. The fact that you multiplied by the 20 didn't change it. The negative did change the sign. All right, we had done that one together. But yesterday, we talked about how one outlier can affect the correlation. Okay, so changing everything, transforming everything, correlation stays the same because that proportionality stays the same. Changing one thing can affect the correlation. All right, down here. Okay, so this is one of the more frustrating things about this unit. I was asked yesterday what is the things I like the best, or what do I like to teach the most and least. This makes this unit probably the one I liked the least because I get most frustrated when you can do well in this chapter if you just learn the facts. Okay, this is not in-depth application of stuff. It's here is a computer printout, and the coefficients are the equations of the line, and the constant is the y-intercept, and that x variable is the information about the line about the slope, and so on and so forth. So that's what is frustrating to me, is when people don't take the time to just learn those facts, then they miss problems of simple identification such as these. Make sure on the bottom question you put that this was 1.97 or 96 crimes per 1,000 in the population. Okay, because that matters. Yes, ma'am. Yes. Okay, next. So these numbers may be a little different than mine, okay, because they can vary slightly. But the idea is that for part A, this should show a number that represents some type of moderately strong positive relationship. This second one should show one that's pretty much weak to no linear correlation. No linear correlation. Now, does that have some type of correlation? Yes, but not linear. The third one is definitely a negative. It looks perfect, so I'd say -1. And then this fourth one should be a number that you think represents a weak negative correlation. So again, your values may be a little bit different than mine, but they represent those ideas. Okay, this problem 8 I love because it really talks about all those changes to correlation and how transformations affect them. So several statements are true. A, B, and E are true statements. A says the correlation and the slope always have the same sign. Okay, and that's true. Now, B is about a transformation. B says the correlation coefficient. So R stays the same no matter which of the variables, X or Y, you decide is the explanatory. So no matter which one you call the X and which one you call the Y, the R stays the same. And that's part of our song. You can add, subtract, multiply, divide. You can even switch the X and Y, and the R doesn't change. So B is true. C is false because of what we learned yesterday. It says the correlation coefficient is resistant to outliers. And that is not true because yesterday we discussed when you've got your data, an outlier, what would an outlier do to the correlation? Weaken it, okay? So one item changing affects the correlation. All right, D, we're changing from inches to feet. That's a transformation. So if we're changing from inches to feet, that's a division. So should the correlation change? If all the pieces of data are being transformed, will the correlation change? That's no. So this says they do depend on it, and so that's why it's false. E, gender, it talks about gender being categorical, so that's true. All right, look at number 9. This is just like what I showed you on, I think, problem 4 on the previous page. The key here is recognizing that this is actual data. So then you know to plug in this actual X to get the predicted Y, and then you can compute to get your residual, which is -2.29. All right, and 10 is a toughie. Yeah. So let me just kind of give you a little word of warning. I'm starting to see a pattern as I go through even AP free response questions. So this is really interesting. I've noticed that we'll sometimes get questions that the question or somewhere it's the definition. So listen to, there's some phrases that should trigger some words in your mind. For example, statement A says about 1/3 of the variation in the Y can be explained by the yada, yada, yada. What do we know is that the percent of variation in the Y that can be explained by the changes in the X. What do we know that to be, definition-wise? The coefficient of determination, that's the R squared. So the key is that language should have triggered in your mind to recognize that definition of coefficient of determination. And so what I thought is, ooh, that's talking about, this says 1/3. Where the heck did that come from? And then I thought, oh, wait, they gave me R, but this definition sounds like R squared. So, I wonder what I would get if I did the R squared, and lo and behold, it's about 1/3. Okay. So that's where that came from. And I noticed on some of the AP FRQs you did in this packet, like I know one of them was question C, I think on page 32. Can't remember exactly, but the question was, what is the percent of variation in the blah, 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 the Y, whatever it was, that is explained by the linear relationship, so on. So The key was, do you recognize this language as the definition of r squared? And then you just said, boom, it's 0.873 or whatever it was. All right, now look at 11. What is this right here? What is that notation indicating to do? This is telling you to transform every x by doing what? Multiplying them all by a negative. Okay, so that's a negative change. All right, what is this notation here telling you to do? Take every y and do what? Add 12. So we're shifting at 12. So this is saying that we've got these two different transformations happening. And what do we know about the transformation's effect on r? No change. However, there was this one negative change. So that's why it went from a negative 0.26 to a positive 0.26. Okay? And then, oh, dang, look at this right here. This should sound familiar. What percent of the variation in the SAT, which is y, is explained by the equation of the line of those two things? The percent of variation, it can be explained by the changes in the x, or it can be explained by the model itself, the linear relationship between those. So it just wanted to know, what is r squared? So I put these into my calculator and computed the r squared. And finally, this one was asking for the slope, which was just r times s of y over s of x. And you know what? You had to do normal model stuff on this page here. I got 2 minutes here, guys, so hold on a second. You had to get a z-score. This had your x, your mean, your standard deviation. You had to get a z-score, and then in probability, remember our P words? Probability, percent, proportion of observations. Then you're going to use norm CDF. So we norm CDF'd it, the upper area. And I'll talk to you guys a little bit about this problem B tomorrow because it's one worth discussing. This 70.7 is not unusual. Hello, it's less than one standard deviation away. I mean, that's just sampling variability. Okay, we'll talk about that a little more tomorrow and go over the other assignments before our quiz.